So, the contrast between interferometric or coherent or field autocorrelation versus intensity incoherent or incoherent autocorrelation is essentially this, that this sort of calibrates itself, whereas this guy needs external calibration. That is the whole point. Of course, we can always ask questions about, is the interferometric way always possible? There may be scenarios where it may or may not be feasible, but that is a discussion for another day. We discussed this table in the previous lecture about correlating pulse widths, autocorrelation widths and pulse widths. Now we come to the moot point, right. So, here we have three scenarios. One is a pulse, a good pulse, a 7 femtosecond secant hyperbolic pulse with a central wavelength of 800 nanometers, which is the wavelength that titanium sapphire femtosecond lasers produce, right. Now, the autocorrelation trace of this pulse with itself looks like this, a nice beautiful autocorrelation trace. Now, consider, are all lasers going to emit such nice, noiseless, ideal, clean femtosecond pulses? No, they are not going to do that. There is going to be the pulse itself. There could also be some satellite pulses owing to various reasons of how these pulses themselves are produced by lasers. There is noise in any physical system, and there could be any other or many other technical reasons. Now, perform an autocorrelation of this pulse with itself, you once again get an autocorrelation trace which is not very different from the case on top, scenario 1, scenario 2, scenario 3. Scenario 1 and 2 are pretty close to each other, because we took this artificial example of a neat clean pulse without any satellites, like in the case 2, we were able to say, this looks nice and this must be a neat clean pulse, whereas look at it here, you still get just one lobe of fringes in the second case, right. So, one could mistake this pulse with some satellite pulses to be a very clean pulse. So, it is not really a process where we basically have a unique solution going from the autocorrelation signal back to the original pulse which we created. But here is the point. What are we trying to solve in this problem? In this problem, we are trying to retrieve this. We do not know this. This is what we are trying to retrieve or resolve. This is what we measure, right. So, how do I uniquely retrieve this? Right now, I am lost for it because of the technique I am trying to use, interferometric autocorrelation, or even this is fringe resolved autocorrelation. The third scenario where I have two pulses, there is some double pulsing going on in the laser, right, for whatever might be the reason. Here I get a triple lobed structure. This we can distinguish from cases 1 and 2, we can, right. We could have simulated things and said, hey, look, this is, you can do this, you can do a convolution of this in your mind's eye and figure out this autocorrelation trace yourself. But between these two guys, not easy, which is exactly the implication of what we stated earlier, that this 1D problem, retrieval problem does not have a unique solution as we want, right. So, what is the way forward, right, or what are the nuances which lead us to this? First of all, why did why did the autocorrelation traces for cases 1 and 2 look identical? In the sense that this autocorrelation trace is symmetric about the 0 of delay. 0 of delay is something we can absolutely fix in the problem. This is symmetric, it is an odd function. Whereas in the time domain, it is not symmetric about the maximum or 0 value for the time scale, which is set by the maximum of the envelope. The pulse is not at all symmetric. On one side we have satellites, on the other side it is flat. So, autocorrelation is the reason. It basically ambiguates this in the sense that we can mathematically show, and it is very easy now to show that the intensity autocorrelation is always going to be symmetric with respect to the delay, because take A2 of tau, per definition it is the autocorrelation of I of t, autocorrelation of I of t with itself. So, it is I of t multiplying I of t minus tau dt. Now, we essentially want to check the fact that this is symmetric with respect to the 0 of the delay, right. So, now here insert a new t prime. T prime is defined with respect to t as t minus a tau. Okay. Now, as a consequence, now just replace the dt's and the t's in the integral with respect to with t prime. Please do this, we are doing this very well, and this integral now from its mere form, okay, both t and t prime are dummy variables, because the integral is going over from minus infinity to both integrals are indefinite, all integrals here are indefinite. So, what is this? This is nothing but, this integral here is nothing but the autocorrelation signal of I of t prime minus tau I of t prime dt prime. This is the autocorrelation of the same thing, but with respect to minus tau. So, these two are the same. Okay. Maybe it is obvious to some of you that it is symmetric, that it is a symmetrizing, it has a symmetrizing feature on it. Okay. It is a little bit like you can take a piece of paper, put some ink on it and fold it up and really press them together and open it. You will always get a symmetric pattern on that. This is something which maybe one did in as whatever, students playing with some paint or whatever it is. So, the whole problem is that autocorrelation has such issues, and autocorrelation says nothing about the phase phi of t function either. So, this is really another thing. So, we have not solved the problem entirely, but we have made progress, but we have certainly made progress with autocorrelation. But look at other aspects too, right. Autocorrelations have considerably less structure than the pulse itself. That is something also which we must realize. Take an arbitrary function like pulse, a spiky pulse like this. There are lasers which produce these kind of pulses, such as free electron lasers. Now, if you do an autocorrelation, it basically masks the fact that this pulse was spiky. It looks like a really nice, a less complicated pulse. It gives us that impression. Again, we cannot invert this back and figure out how complicated life was in terms of the pulse itself. That is a big problem, right. So, what is the problem with submitting ourselves only to autocorrelation? The autocorrelation trace in a scenario is not unique to a pulse, but we want the we want a unique identity for each pulse. That is metrology. We want the Aadhaar card of each pulse and know its entire, get its entire identity, and it has artifacts when it tends to be incomplete, right? And there are other issues like higher order autocorrelation requires that the primary pulse itself be strong enough to produce a reasonable higher order autocorrelation signal, right. So, autocorrelation is a very useful tool to know something about the pulse rather than do a complete pulse metrology and a test of things, right. For example, just to drive home this fact, look at this really somewhat ugly looking set of pulses. Start from the one, say at the very bottom. It's really rubbish, right? Spikes, sets of spikes. This is not like any laser pulse should be. This is just I'm only talking about the intensity profile. High frequency is associated with noise typically, right? It's a very noisy pulse, but look at its autocorrelation. It masks the fact that the pulse was so spiky and noisy. It gives it a smooth profile with a little feature on top of it. Take another pulse which is less noisier, but even then it gives a symmetric autocorrelation trace, which one may associate with just one broad pulse structure and another narrowish pulse structure. And without too much insight, we can say that this autocorrelation belongs to a pulse which in time has this kind of a structure. There is a shorter feature and a pedestal and a taller feature, like maybe a spire structure of a monument or something like that. So, the whole point is that the spike produced here, okay, in these cases this tall spike which we produce here is called the coherent artifact. Which is to say that the coherent artifact is simply measuring for us what is the narrowest structure in this pulse, that is all. It is just giving us some information about that. Okay. Furthermore, imagine a scenario where your detector has a limited dynamic range and it could only measure intensities above a certain point, above a certain level, in which case the bottom of the iceberg is totally submerged under noise, and we could mistake this coherent artifact to be a nice neat short pulse. There is all these kinds of ambiguities which pose themselves in the context of autocorrelation of very complex pulses. Thankfully, modern resonator based lasers produce pretty neat pulses when they work fine. That is the beauty of the mode locking process, which we have not discussed much in this course about, but that is a good thing. But that is a fairly narrow or a small island in which femtosecond pulses live. If you looked at nanosecond pulses which come out of Q switch lasers, there of course you have the benefit of doing some direct time measurements with fast diode detectors, but if you applied the same logic, then it would have been very misleading. The Q switching process produces satellite pulses by its very way of working. Or take modern free electron lasers which are mirrorless lasers in the modern free electron lasers in the vacuum ultraviolet, soft X-ray or extreme ultraviolet. They are also lasers because they operate by amplified, they basically also take advantage of stimulated emission to exploit gain, that the gain medium is a propagating electron beam and so on, but they do not have the benefit of a resonator and they do produce such noisy pulses. You can do autocorrelation measurements with them and be misled that the pulse is fairly neat in its temporal structure. That is not the case in fact, and in fact pulse to pulse variations in the profile of these free electron laser pulses is a matter of concern and something that practitioners and researchers are having to live with as we speak today, right. So, with all this happening, a mere gamma of t measurement or an intensity envelope, for example, the way it appears over here when we plot, is quite a misleading thing, if we rely entirely on just the linear or other low orders of autocorrelation, just second order or third order. They would all give us these kind of misleading insights into the time structure of a pulse, noting for the fact that the intensity autocorrelation is simply this sort of an integral, right. Very well then. So, this in a way is an expression of the fact that retrieval is, we are failing to do unique retrievals as we would have liked to want. I mean, just to sort of impress this upon you, determining the structure of a DNA through crystallography was also a retrieval problem. It turns out to be one of the most important retrieval problems or inverse problems in history. Imagine if we had ambiguities about it and did not have unique retrievals possible. There would not be the whole field of molecular biology and maybe even some advancements in medicine and stuff like that, right. So, that is how important retrievals turn out to be, right. So, there are other issues like double pulses and mistaking unstable trains of pulses from lasers and misinterpreting autocorrelations from such sources, right. So, the interferometric autocorrelation problem itself has quite a bit of several ambiguities, right. So, for both types, both of these pulses, look at this pulse to the left, it has a slightly asymmetric Gaussian profile in intensity, whereas a flat phase profile, whereas here the phase profile is not flat and the intensity profile is fairly symmetric. Their FWHMs are also apart by about a couple of femtoseconds. An interferometric autocorrelation with either this pulse or this pulse will look really nice and cute like this, if I may say so. It looks like an extremely well behaved sort of pulse. These two fairly different pulses have nearly identical interferometric autocorrelations, and understand the fact that these are real world experimental measurements. This picture is actually contains experimental data from this paper from Andrew Weiner's lab, but it is actually really beautiful, very low noise data. That is why it looks like this. You may or may not always be able to get this data quality, right. And the coherent artifact makes life fairly miserable. I mean, look at this pulse if you wish, really somewhat spiky, even spiky ugly pulse has an interferometric autocorrelation which is dominated by the coherent artifact. This is really a problem. From this, would you have guessed that this is the pulse that produces this? No. We would have ascribed a much simpler structure for the amplitude part. Both the amplitude and phase are quite noisy. Therefore, what can we do to remedy this situation? Right? We wish acoustics were all we had to deal with, where we have really fast detectors and we can do everything away with, right. So, acoustic detection was also advanced by very clever people like you. So, I am sure that this would have piqued the interest of any clever engineer or scientist working at that pioneering stages of this field of development. So, let us see how to go about that. What is the way forward? Yeah. So, the next couple of 10 minutes on that. Spectral methods. We have so far not used spectral information efficiently. Maybe if we use spectral information and do interferometry along with it, perhaps there is hope to move forward, maybe even do complete pulse metrology. right. So, can we not? So, whenever we hit a dead end in a scientific problem, what do? We should go back and examine first principles, right. First principles of practically everything, isn't it? Even if it's rocketry, right? We need vertical landing and reusable rockets. Someone questioned the fact that rockets should have to be sent away and thrown away in space and not be reused, because of which costs are huge. But in the current era, we have the scenario where we bring back the rockets and reuse them, because people elsewhere, I don't want to take names, but you understand that great minds examined the fundamentals and first principles and got this back on track to have some breakthroughs in that sense, right. So, whether it is that or electric vehicles or whatever else, there is merit to the physics based approach of going back to first principles, then putting that in the context of current technology and looking for new advancements and pushing the frontier of knowledge, right. So, essentially what are we doing with pulses? We have a fair idea of that. So, in terms of taking things apart and looking back at it in terms of first principles, let us simply look at the fact that and appreciate the fact that a pulse is a time frequency entity, right, because a linearly chirped pulse has a temporally varying central frequency. The instantaneous frequency varies linearly in time. A quadratically chirped pulse has quadratically varying frequency, instantaneous frequency quadratically varying in time, right. So, time and frequency are the two important characteristics, time and instantaneous frequency are the two important characteristics of a pulse. But again, going back to acoustics, that is a musical score, right. A note, a note, a note, a note, a note which is being played. I play no musical instrument, no tune instrument in my life, so I have absolutely no idea what these notes turn out to be, but written down, an expert hand and more can play out the sequence of notes and produce music, which is a time frequency information in the temporal hyphen frequency domain, right. So, also the notes of Indian music, their frequencies are related in ratios. If it's saga pa, it's 4:5:6, right, and so on and so forth, right. And there are 3 variants of each of these notes which are well codified and documented, right, and so on and so forth. Every musical school or system has all this very well worked out. What have they worked out? They have worked out the frequencies. A box like this can produce these frequencies at will, which is the Indian version of a piano if you wish, but much less expensive than a piano. But then you can press these keys in varying time durations and produce music of the type that we like or we would like to listen.